Second, Wilko, you are the chair, and you are not there. You are online. We don't see you. So I will be acting chair, and I will give the word to Jnandeep for the master participant. The committee consists of Wilko, who is chair, of Stefan Luding, of Vatsal, and of me. And we have a guest in the committee, Sarah, who will ask 9 questions. This is fine with you, right? Yeah. Yes. The way you must be intellectually entertained, and we will all contribute. Yeah. Okay, go ahead.
Yeah. Thank you, Detlef. I'm Jnandeep, and welcome to my master's seminar. And today I will be talking about singularities. I will also thank people who are directly involved in this project, who are PhD and Vatsal. And along with them, I use Aman's really for really nice discussions. And while I was in London, I also had really good discussions with Omar Makar and his group, and also Ori and Darren from Applied Math Department. So I would like to start with a really beautiful video where there's a drop which is sitting on the roof, and there's a drop that impacts on it, it spreads, and then it merges into one. And this phenomena it occurs everywhere. You open a tap of water, you see it. It's raining outside, you see it there. It's everywhere, and also it's a very common phenomena in the industry too. And this phenomena doesn't just happen with drops and drops. It could happen with a drop and a bath. Yeah, and then it could be drop, which I showed you. It could be between bubbles. It could be also between liquid lenses, which is basically, let's say, oil droplets on a bath. And in fact, one of the earliest study was based on this drop bath configuration, and it was done by J.Z. Thompson back in 1886, and where he talked about this drop impacting on the bath and forming these beautiful vortices that you see here. And this was done almost a decade prior to him discovering the electron. So this dates back quite old. But today we'll not talk about this configuration, this drop bath configuration, but we'll talk about this specific configuration, which is sessile drop configuration. And what I mean by sessile drop configuration is basically you have 2 drops. You can see the top view and the side view. These drops come together, form a liquid bridge, and then they merge into one single drop. It's very easy to visualize. Also, like experiments clearly show that it comes together, forms a bridge, and then it merges into one. We go into a bit more detail. So let's see what's happening in the neck. On the neck, what we have is there's a neck which has a negative curvature, and because of this, capillary doesn't like it, and it wants to fill the neck from both the sides, and it's symmetric from both sides. But what happens if we introduce 2 droplets which are miscible, but they have different surface tension? And now what you see is that you have on the left gamma 1 and gamma 2, and your right drop B has surface tension gamma 2, which is bigger than gamma 1. Now, if I again look at the bridge, similar dynamics happen, that we have capillarity that wants to fill the neck from both the sides, but there will be asymmetry because of this magnitude, this difference of these surface tensions. But along with this, another component comes in that also breaks the symmetry is this Mann-Goni force, which wants to suck your liquid from A to B. And how does it look in the experiments? Is this critical phenomenon which happens is that instead of these drops coming together and merging into one, it instead pushes the other drop and it doesn't coalesce. At the later stage, it coalesces, but at the initial stage, it pushes the other drop. Now, why is this relevant? It's very much relevant in industries, more specifically in the inkjet printing. And you could see this really nice schematic from Detlef's annual review. This is basically inkjet that is being jetted out, and it falls on this substrate, which we can think of as paper. And once it falls on the paper, you could see at drop 6, at process 6, it interacts with its surrounding drops. And what could happen is that let us say that this is a red drop and this is a blue drop, and when they spread on it, instead of spreading nicely, it pushes the other one and it ruins your film quality. And you could think of it like in inkjet printing, there will be not just 2 drops, there will be like hundreds of thousands of drops. So you can imagine how the print quality could go in if we don't understand this process. Further on, it also is relevant in biology. How come? So basically, if I show you here, we have this cell, which is an NC cell, and this is a mesothermal affinity. And it basically, this NC cell encompasses this drop. However, in here, if you see, if it's two same NC cells, they have this contact inhibition. Basically, they don't engulf and they push each other. And what people try to do is this called as original of light prototypes, which is basically you have drops which replicate cells. So people, what they do is like they have these drops, and they have this two drops with different surface tension, and one of them changes another. Well, onto this menu, I don't talk about binary drops with two different surface tension, but I talk about what happens when you add surfactants to it. And what happens when you add surfactants to it is that now my surface tension is not just two values, gamma 1 and gamma 2, but my gamma is also a function of my surfactant concentration. And just a very quick disclaimer is that I won't be talking about the top view. So what I mean is that my drops would be basically cylindrical drops. So you could always think of that instead of two spherical drops coalescing, it's like a primer which is coalescing. Back to the thing. What I have in the setup is that on my left drop, I have surfactants, so it's a dirty drop. On the right, I have a clean drop. And basically, when you have surfactants, you can also adjust on your interface, and basically it diffuses, it converts with, and it diffuses with the diffusion coefficient of ds. And what is not onto this menu is the numerical framework and the simulations that I use. So I use a finite element code file, which is developed by Crystal and Duarte, and all the codes are openly available on GitHub, so you can always scan them. Okay, so how do we model the system? First of all, we talk about viscous and low contact angle drops. So we can always assume a lubrication approximation, very good. And for our surfactants, we use a transport equation, which is this. So you can see there's a convection term and there's a diffusive term. And if I merge it together, so we have this lubrication equation, we have this surfactant equation. So this is your hydrodynamics, this is your surfactants, and how do you couple this is using a linear relation between my surface tension and my surfactant concentration. So it's a linear relation, and it works in this value region of 0 to gamma infinity, beyond which my linear model fails. So we don't go towards that. Next, what we do is we non-dimensionalize everything with respect to viscocapillary time and radius as the length scale, and we arrive at this equation. So this is my non-dimensional equations. You could see there's two parameters that pop up. One is a beta, which is your surfactant strength. So it basically tells you how strongly your surface tension will change when you add surfactant. So more beta means it will change more with respect to your surfactant addage. Next is your Peckley number, which you see in the transport processes. It's the ratio of advection to your diffusion. And more Peckley means it will be that your surfactants will be advected. And if it's less, then your surfactants will be diffused. And further on, one parameter which is missing out here is this contact angle theta, which is basically your interfacial contact angle when these two drops come together. Well, so we have three parameters, but to make life easier, what we do is like we keep our theta fixed and we just focus on these two, which is Peckley and theta. And another disclaimer is that it's also a popular number, Marangoni number, which is basically the product of my beta and Peckley. So if someone is used to Marangoni number, then they can always think of it as the product of my beta and Peckley. So we start out with this parameter space, beta and Peckley. So we start with low Peckley, and you can see this is your neck, which is by this red dot, and it just moves upward, and your just neck moves upward, and it looks more like a coalescence type state. So we roughly call it coalescence. Next, we put our Peckley higher. And what happens when you put Peckley higher, you could see there's a significant movement of the neck towards the right. It still vertically goes upward, but we roughly call it non-coalescence. And why this happens is this analyzing your surfactant profile. You have your surfactant profile, so this is 1 on the left and 0 on the right. 1 on the left, 0 on the right. And for your coalescence case, your surfactants diffuse very fast. So you see this coalescence type state. However, for your higher Peckley, your surfactant profile is more sustained for longer, so you have manganese stresses, and that drives the neck towards the right. Well, and this is the whole parameter space that we would like to think about and would like to study now. So I start with the low Peclet case. So what I mean by low Peclet is that what happens when your surfactants diffuse very fast. Again, I show a typical schematic of your low Peclet case. And as I have shown you before, it shows more like a coalescence type behavior. Your neck just moves upward, and then it merges into just one single drop. And if you look at the left, it's H0 versus T, which is the height of the neck, and it follows a linear relationship with time, which is well known from your classical coalescence of pure Newtonian drops. It follows the exact simulation. So, okay, this on the top of the hat, it follows coalescence type behavior. Does the flow profile also look the same? Also look similar? So for this, we plot these velocities and we plot velocity plots, velocity vectors. And on the interface, I put the surfactant concentration. So one is surfactant, one is black, and 0 is white. And as you can see, it instantly diffuses, and your flow is directed towards the right, towards the neck, and it just moves upward. But one thing which is indispensable here is that you start out with this 1,0 profile, and it diffuses to this half value, which is 0.5. So can you understand, or can you predict this initial surfactant diffusion? And to answer this, what we introduce is this temporal boundary layer. And what I mean by temporal boundary layer is very much similar to your spatial boundary layer in turbulence. So how is it similar is that in this boundary layer, which you see here, which is a representative diagram, inside the boundary layer, in the inner boundary layer, you have manganese stresses, and outside of it, you don't have manganese stresses. It's very much similar to your spatial boundary layer, where inside of it, you have viscous stresses, and outside of it, you don't have viscous stresses. And what I mean is that by saying that there are manganese stresses, is this basically within your surfactant, within your depth, there will be your surfactant will diffuse and it will become uniform. And this thickness of this boundary layer, I denote it by tau. And once we go above it, we see this surfactant profile, it diffuses, so we don't have any manganese stresses. So it's very much similar to your boundary layer in turbulence. Further on, now we'd like to express this thickness in terms of Peclet. So we do scaling for this. So we have a convection time scale, which is a visible capillary time. We have a diffusion time scale, which is this. And based on this, we get this diffusion time, and our tau now scales as Peclet. And why we introduce this concept is that it's very much similar to how people do it for turbulence, where they regularly perturb your velocity field. Now here, what we do is that we perturb our two different fields, which is the height and our surfactant concentrations. So yes, so what we do is we do regular perturbation in H and surfactant concentration. And the following analysis, which I'll tell, comes from the regular perturbation analysis, but I would like to show you it in more terms of physical intuition. So let's say we start with our surfactant profile, and it's very easy to understand that if you have low Peclet, your convective term will go out, and then it becomes a linear conduction problem. And it's basically like you have two plates, one is at T0, one is at 0, and how the profile evolves, which is given by your error function. And how does it look with my numerics? You can see at T equals to 0.5, which is at the early time, it matches quite perfectly. But as I keep on increasing my T, the nonlinearities start kicking in, and at the extremities, you don't see it following well. But the thing to note is that my neck lies at 0, so it's still a good approximation for my surfactant profile. Next, we revisit the height profile. So we have discussed that the height follows linearly with time. So now I plot height versus time again, but for different sets of parameters. I vary both beta, Peclet, and theta. And what you could see is that this patch of this shade of blue, it appears here, and this shade of green, it appears at the top. So what it basically means is that your H versus T, it doesn't quite depend a lot on beta and Peclet, but it has a strong dependence on your theta. So if you move from theta equals 10 to 20, it moves with this curve, but with beta and Peclet, there is almost weak dependence or no dependence. So to understand this, we again go to our height evolution equations. You could see there's two terms. So this is the two fluxes that wants to increase the height, and on the left, which is the capillary flux, so it wants to push your neck upwards. and your manual fluxes will be dominant along your substrate. And based on this, what it means that at early times, your capillary fluxes will be dominant and it will move it upwards. So what we see is this, we can ignore this manual term, and also comes from our perturbation analysis, is that, okay, we can ignore this term, and this is our set of equations that we have to solve now. And for this, what we do is we introduce a similarity variable, zeta, and then we introduce this high-fidelity similarity equation, and then it just this whole set of PD, it sublimates into this one single ODE. And we put boundary conditions and we get H naught as this. So as you can see here, it has a strong dependence on theta, which is 4, and it has a very weak dependence on beta and no dependence on your capillary. So how does it look on my profile? Is this, so we have this H naught versus T. Now if I compensate on my y-axis this factor, you can see it collapses quite well for both of my catches of H naught. And along with that, this red line, which again comes from theory, it matches quite well, and it's without any adjustable parameters. Next, we move. Okay, we talk about this vertical movement. Now we talk about this horizontal movement, and so this horizontal movement, I characterize it by x naught. So this is x naught versus t. And unlike the last time, there's two significant observations first. First is this, it follows the TH for 3/2 law, which we don't understand. And the other is that if we vary beta and Beckley and theta, it's all over. So it basically means that it has a dependence on your beta and Beckley. So to get this, what we do is we look at the surface velocity. And the surface velocity is again composed of two terms. One is your Laplace term and other is a manual term. And again, the same regular perturbation analysis, that it's at your early time, your Laplace term would not be dominant, your manual term would be dominant, and it will drive the neck towards the right. We do this, we do a bit of calculus, we take the leading order approximations, we arrive at US, and then we integrate it and we get x naught. So you can see for x naught, we get TS for 3/2 power law, which we had seen in our plots, and we also see dependence on beta and Beckley. Again, how it looks on my plot, it was all over. Now I compensate this with my prefactor, and you can see it collapses quite well. And also this line is again from the theory with no adjustable parameters, so it matches quite well. But so we talked about this neck, which moves towards the right. But when does this neck stop? Like when does it reaches a maximum horizontal movement and it now turns back? So to understand this, we look again at the neck. So at the initial, what you have is this asymmetry in your Laplace and your manually, because there's a gradient of your surfactant profile, and it drives the neck towards the right, which you see. And once it reaches a stage, it starts turning back, and this stage where this movement is called, we denote it by XF, and why it turns back is basically now you have asymmetry in your geometry, and this also creates asymmetry in your Laplace forces, and your neck starts moving towards the left. And this is well explained by this PRL of Yakoyama. Okay, so now this XF, which is the maximum movement that we talked about, how does it vary with Beckley number? So well, we start with this low Beckley, and you can see as you keep on increasing our Beckley, XF starts increasing, which makes sense because if you keep on increasing Beckley, your diffusive time starts increasing. You'll have manual stresses for longer, and your XF will increase. Makes sense. And now we keep on increasing our Beckley. You can see it's still increasing, like with Beckley increasing, your XF starts increasing. However, for this particular case, which is 0.15, you see that there's a non-monotonicity. It starts decreasing and then it starts shooting up. And if I go for lower than this, so this is beta 0.15, and I go lower than this, which is 0.1 and 0.05, what we see is that instead of beta going up, XF going upwards, it starts going downwards. So what it basically means is that if I have a drop, when I increase my Beckley number, and if the beta is below this critical beta, then instead of going towards the left, it just goes vertically upwards. There's no existence of XF. So this I'll keep it for later. First, we try to understand what's happening in the low Becquerel regime. Again, in the low Becquerel regime, we try to see how XF varies with beta. And you can see if XF varies quite linearly with beta. And we understand this again. So what we do is we have simple scaling analysis. We have here velocity scales, which is capillary on the vertical and manually on the left. And we have a diffusive time. We calculate XF, which is basically your manually times diffusive, and we get XF as beta times Becquerel. So now when we compensate this with beta, it collapses quite well. And also, if I also try to plot this Becquerel line, it also follows it quite well. And another thing that I like about this plot is that once you compensate this, you can see that this follows till here, and from here it more or less starts showing some different behavior. So this allows us to bifurcate this into two regions. One is this low Becquerel region, and the other is your high Becquerel region. Now, I've talked about this weird behavior that we see for high Becquerel cases. Now we try to understand this. So what sets this non-monotonicity for your high Becquerel cases? And so you ask this question. And to answer this, we take two cases. One is your beta 0.5 Becquerel 1000, and your other is beta 0.1 and Becquerel 1000. So basically, in the other two extremes of your plot. So let's start with beta 0.1. So let's just look at the flow profile for beta 0.5 and 0.1. So you can see for 0.5, there's a manually flow that is driven towards the right, and your neck moves along with it, which is pretty much expected. But for 0.1, you can see there's still a manually flow that is directed towards the left, but your neck, instead of moving along with the flow, it just opens up and it moves vertically instead of moving towards the left. Towards the right side. So to understand this, so we try to look at the surface velocity. And the surface velocity, as I've shown you, it has two components. One is the Laplace component, which is this, and the other is the manually component, which is given by purple. And for low Becquerel cases, if you remember, you had only one of the terms which was dominating, which is this your manually term. And for your high Becquerel cases, both of these terms dominate, which I show you by this plot. So on this plot, we have US, which is the surface velocity given by blue. You have orange, which is your Laplace component, and you have purple, which is your manually component. And you could see, so your Laplace manually component is positive, your Laplace component is negative. And since your manually component is not positive enough to make your US go up, so basically there's existence of the positive velocity and the negative velocity. And what it does is that, so yeah, the manually is not strong enough. And what it does is that there will be a bidirectional flow. So on the left, your surfactants will try to diffuse towards the right, and on the right, the surfactants will try to diffuse towards the left. And what happens, what's the implication of this is that if you look at your surfactant profile, this is gamma, and you see, so there's surfactants are pushing towards the right, and this on the other side, the surfactants are getting pushed towards the left. And this creates a distinctive slope that you see here. And because of this slope, you see two slopes. One is this one, and the other is this one. So this is a positive slope, and this is a negative slope. And because of these two different slopes, we get two different stresses. So if I plot the manually stress now, so I have positive manually stress, which is high here. And along with this negative positive manually stress, we also see this negative manually stress that also exists now. And basically, your movement of your XF of your neck, it doesn't move with just one peak, but it's a balance between this positive and your negative peak. However, for 0.5, what we do is by increasing 0.5, we increase our manually component. And when we increase our manually component, you can see it's strong enough that your US is always positive. So your US is never positive for any space and time. And what it means in our flow profile is that your flow profile, your surfactants will always be convected towards your right. That's right. Yeah, so your surfactants are always driven towards the right. So there's no peak that we saw for the hydrogen one. And basically because of this, our manganese stresses is just one single component, which is a positive component, and it goes by this positive peak and it just propagates towards the right. Another reason why I showed this manganese stress is this manganese stress leaves a fingerprint, or more specifically, negative manganese stresses leave a fingerprint. And what we mean by this is basically if we take a macroscopic volume with volume V and surface area S, and we try to calculate the vorticity generation, it has basically three terms. One is because of the gradients, one is because of the viscous layer, because of the viscosity, and the other term is this. You can see there's a T term, which is your manganese stress. So this is negative T. So basically, negative manganese stresses will create a positive vortex, and your positive manganese will create a negative vortex. So yeah, negative manganese stresses generate vorticity. And you could very well look for point 1, where we had this existence of negative manganese stresses. There's a positive vortex over here and negative vortex over here. However, for 0.5, we don't see any such significant vortex. Now we push our packlet to higher packlet for point 1. And we again plot the same thing. We plot our velocity contours and we also plot our velocity vectors. And since beta is 0.1, you are expect the net to move upwards instead of moving towards the right, which we see here. But along with this, what you see is that there's a soft solution that propagates towards the right. So first thing that they asked is this soft solution numerical. And for this, what we do is that we have our Stokes equation, we have our surfactant induction diffusion equation, and Hayes et al. Have shown in a series of 2 papers that if you have this set of equation, you can write your surface velocity, which is this, as a Hilbert transform of your surfactant profile. And when you do this, you basically transform this from a 2-dimensional problem to a 1-dimensional problem. And recently, probably showed that if you have this set of systems, this set of equations, and you take a complex function phi, which is composed of your real part US and your imaginary part gamma, you could sublimate your surfactant induction diffusion equation into a complex Burgers equation. And for this, you could see if I have higher packlet, this right part is nullified and it becomes basically an implicit Burgers equation for which soft solutions could very well exist. Further on, do people also see it in a physical setup? So the answer is yes. So basically, if you have a drop which is spreading on a surfactant-laden drop spreading on the substrate, you could see they have a surfactant profile that looks like this, and you get a kinematic shock, and you also you can see that there's a layer formation over here. And it also looks like it's an experiment where there's instabilities over here, if you gain instabilities, and there's black layer, which is basically limits this relationship. And also further on, people have shown in more other settings that soft solutions are possible. And in my setup, how do we see it? Is this? If you look at it, it looks very much similar to my surfactant profile that people have shown it before. And this is the shock front. And if I have bifurcated into minus plus, at the left end, you see you have a surface gradient. We have a surfactant concentration gradient. We also have a finite surfactant concentration, and this gives rise to US minus. And on the right, you see that your surfactant concentration and your gradient is both 0, which gives it US plus, which is your which brings the discontinuity in your surface velocity. Further on, what we do is we push for more packlet. So what we mean by more packlet is basically we set this term 1 by packlet equals to 0. And so in terms of equations, you could look at it was this term. So basically we turn off this diffusion term. And this is my high evolution now. And this is my surfactant evolution. So for high evolution, which you see now is that this drops, they move as if they are like twins and they move towards the right. And the neck, which was here, it doesn't open up towards the vertical line, but it just moves towards the right. And your surfactant profile also is it's convected towards the right. And this gives us an idea. So we plot x0 versus t. So x0 is again the movement of the bridge towards the right, and it's fairly linear. And why we want it to be linear is that once you have a constant velocity, we can now write this down as your traveling wave solutions. So inspired by this paper, where we have these traveling wave solutions to your tilt locations by Stefan and Prof, we do the same analysis. But now what we have is that we have two systems. So we have a drop, which is doing drop, and it moves with this velocity dn. And for this, we have this stable traveling wave solutions. And we also have a surfactant profile that moves towards the right. So for this, we have a moving solutions. And once we couple it, we get this set of equations. And what this set of equations is that it's very much similar to your Tanner's law, which you see. But except in Tanner's law, this component is just one parameter, which is d. But for us, we have two components, dn and d gamma, arising because of your twin drop movement and also your surfactant profile. Now, trying to understand the stability of these solutions is very interesting, because when you have high Becquerel, or let's say in this infinite Becquerel limit, you could think of that. Let's say if you have beta, which is greater than 0.15, you have a finite XF, or you could say that your drop moves towards the right. However, for beta less than 0.15, you see that your drop doesn't move towards the right; it just vertically goes upwards. So what it means is that if it's your beta is greater than your critical beta, you will have your stable traveling wave solutions. And if you have beta, which is less than critical beta, you have unstable traveling wave solutions. Next, what we also do is that, okay, so we have our set of equations. We want to do a singularity transform, just like how we did for our low Becquerel cases. And since we don't know the exponents now, what we do is like we take a general ansatz, which is h0, phi0, and a singularity variable, and we just put it in, and we assume that your h0, x0, and your thickness all is a power law of your in terms of the time. And once we substitute this to get consistent self-similar equations, we get this. So basically, your h0 should be linear, x0 should be linear, delta should be linear, and your surfactant profile should be independent of t. There are two good things about it. First of all, it's x0 is linear, which means which is what we also see. So x0 is proportional to t, which you see. And the other term, which is this, it basically means it's independent of time, which also makes sense, because since there's no diffusivity, your state profile will more or less remain the same height, but it just convex towards the right. But the other delicate term is this h0, which is basically it's proportional to time. But what could be that is that this coefficient for your time, CV, it could be very much smaller than your coefficient for your horizontal movement. And so in our equations, we just don't see this net going upwards. And based on this, we put our ansatz in this, and we get this huge equation. And if you look at it closely, we see that your H is a fourth order, is in fourth order, phi is a third order, and you also don't know two parameters CV and CU, so you need 4 plus 3 plus 2, which is 9. So you need 9 boundary conditions. So yeah, it's a lot. And so yeah, while I was sitting down, I was trying to solve it. My time ran out for my master's assignment, and I think it also did today. So I'll just give you a brief summary about what I talked about today. So for low Becquerel cases, we showed this temporal boundary layer, and through this we calculated this. It's not as an analytical expression. We also calculated an analytical expression for x0, and we also gave it scaling analysis for your maximum horizontal movement. And for higher Becquerel, more interesting physics comes up. We see that once you introduce surfactants to a coalescence case where there's interesting dynamics still happening, but once you put surfactants, you could see these air set states where there's non-monotonicity in your Becquerels. And you explain this to our surface velocity. We show that there's vorticity generation. Along with this, we also show that there's some existence of flux solutions, and we also show that it could be also approximated with some traveling waves. So yeah, with this, I would like to thank you everyone for your attention, and yeah, I'll be happy to take questions.